should be able to keep up because you have like two different forms of the videos from two different classes, okay? So no excuses.
No didn't. Nice hack.
So, 13.3. What's it all about?
It's about 13.3.
Arithmetic and geometric series. What's the difference between a series and a sequence? That's the only difference. I know they're very similar sounding words, and in English class you probably wouldn't make a big difference of it. In fact, the World Series is a sequence of games. Okay? So that's what I'm getting at. They're kind of synonymous, but no longer. When I talk about a series, it means the sum of the terms in a sequence. So get that idea down. Now that's what happens with a finite geometric series or arithmetic series. Hello.
Wait, so series aren't inherently
No, they could be infinite. And that's what our next section is going to be about, is infinite geometric series. Right now we're just going to focus on the finite series. Okay, give me a finite, fixed number of terms off of a sequence and add them up. Okay? And these are two examples of infinite sequences versus the series that goes along with it. This is arithmetic over here, this one is geometric. But you could have an infinite arithmetic sequence. We don't study those so much because they get so huge. What's an arithmetic sequence that doesn't change in size? Is that arithmetic? 5, 5, 5, 5, 5, 5,
It's
5.
not, there's no difference.
Has a common difference of 0.
Yeah.
It would have an infinite sum if you try to add them all up. You can also look at 5, 5, 5, 5, 5 as geometric. The common ratio of 1. Right. Now, here's what we mean by S sub n. This is called a partial sum, as opposed to the infinite sums we'll do in the next section. A partial sum. So it's not the sum of the infinite sequence. This is the sum of just the first n terms of the sequence. That's what S sub n means. Now, you can define S sub n recursively with this idea. S sub nothing, basically I put it in there just so we can start the recursion. S sub 0 equals 0. In other words, I'm not adding up anything. But S sub 1 will always just equal the first term in the sequence. Because S sub 1 and T sub 1, actually it's one time they're the same thing.
Wait, so
But S sub 2 is S sub 1 plus T sub 2. Joey?
so is S sub 0 always 0 then?
Yes. Unless you have, your sequence doesn't start at 1. I just have this be 0 so they can refer to S sub 1 is basically then S sub 0 plus T sub 1. Right? I could write it that way too. S sub 1 could also be thought of as S sub 0 plus T sub 1. S sub 0 is 0 plus T sub 1. It's just to get the sequence started. So you can define sums recursively. Keep that in mind as we investigate, especially next section, that instead of having to, if I'm trying to add up the first one term, then the first 2, then the first 3, then the first 4, then the first 5, then the first 10. If I've got the sum of the first 9, I'm not going to re-add those. Right?
What do you mean by recursive?
This is the recursion right here. I'm referring a partial sum, S sub n, the sum of the first n terms, is the sum of the first n minus 1 terms. So I'm referring it back to original.
So like, I don't know what's the definition of recursive.
That was section 2. You were here, right? Or were you gone? You were here that day. We did notes on section 2. Recursive definition.
Bill doesn't take notes.
No, he won't. It's a good question. Recursive implies that you're referring to a previous term to find the next term in the sequence. Explicit is when you just define it in terms of n. Okay? That's not what we're doing here. This is a recursive formula. We're referring back to a previous sum to quickly come up with the current sum. And this is a universal idea for all S sub x, no matter what kind of sequence, arithmetic, geometric, or neither. You find the sum in the sequence by adding up the first n terms. That's sort of the explicit definition because it's done in terms of every single term up to that point. The recursive idea, though, is to define it in terms of the previous sum. Okay. And I'm actually, sorry about that, I'm going to cross off this word explicit definition because that kind of implies it's just in terms of n. And we'll have some explicit formulas like S sub n equals n times t1 plus t2 over 3. This is, let's just call it the basic definition of S sub n. It is the sum of the first n terms of a series. Okay? All set? So example 1, find the sum of the cubes of the first 20 positive integers. By hand? Oh shit, we know our cubes, right? 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed, 6 cubed plus 7 cubed plus 8 cubed plus 9 cubed.
Stop. Looks like a 2. That's 2, 7 to 8. Why not just put us a calculator?
Exactly. Okay, Bill. All right, I'll go with that. If you all have your calculators handy. I don't see them. You want to do this on a calculator? Well, where are they? You should have a little spot in your belt right here to carry your calculator around, okay?
Yeah. Where are you going?
Instead of stowing your backpack, leaving the lobby. Somebody took it, I wonder why. When I bike to school. I did today. So let's try it with the TI-89.
We need some sigma.
Real easy command. Get used to this symbol. This is the Greek letter sigma. There's an actual fraternity called Kappa Sigma in Madison. Right? So, there are others. And we picked this because it's the Greek letter for S.
Where is sigma?
Sum. Right? That's why we did that one. Okay?
Catalog?
No. I say right here, Joey.
Oh.
You can find sigma in your catalog or in the S section. You go down to the S's. Or F3 calc, and then you've got it right there. You can just go, if you're on the home screen, just hit F3 under calc, because this is a calculus concept now. We're actually starting some calculus ideas. Okay? Sigma. Now, you've got to put a formula in. You don't have to use n. If you find it easier to use x, that's fine, as long as you're consistent. You specify your index variable here. In fact, we're going to have a later chapter where we talk about sigma notation. Summation from n equals 1 to 20 of n to the third. That's called sigma notation. We'll have a whole section on that later. But I thought you should get used to how you can do it in your calculator. Yeah. Let's just make that a little larger, Joey. Yeah,
Why is n equal 1?
No, n goes from 1 to 20. Because basically we did t sub 1 plus t sub 2 plus t sub 3 and so forth. Okay? Now, that's a handy way to check work, but I expect you to be able to do this without the calculator well. This one eventually too, because we're going to come up with a formula for the sum of the first n cubes. Would you like to see it?
I would. Yeah.
You'll have to wait.
No.
Later we'll do the formula for the first n cubes. For right now, find the sum of the first 100 natural numbers without a calculator. Carl Friedrich Gauss did it. You can do it too, okay? You did it in primary school, okay? The young Gauss repeatedly produced the correct answer within seconds to the astonishment of his teacher and his assistant, Martin Bartels. An ancestor of Dr. Bartle over there, okay? So what's the trick? Or get busy. Solve's calculator. What's the sum of the first 100 numbers? Sum of the first 100 numbers. Not 550, no. That is not a refreshing calculator. 5,050. How do you get there? How do you do it so quickly? 1 plus 2 plus 3 plus 4 plus 5 plus
It's 1
plus 50. Hang on, plus 51 plus 52. 98. 99. You just have to do the wraparound thing, right? If you do it like that, and now because the commutativity and associativity of addition, it's 101 and 101 and 101 and 101 50 times because we have 50 pairs. 50, 50. There you go. Well, that's what Gauss came up with in primary school. Of course, does it say primary school?
Yeah, that's the first time.
Primary school could mean up through 8th grade. Isn't your secondary school now? So he might have been 8 years old. He might have been in 8th grade. Primary is elementary? Okay. So up to 4th? Your tertiary school? I think this is secondary education.
We're in secondary. Yeah. I guess.
So, hey, Gauss, we're still impressed.
Okay, so we did.
Did you get an answer akin to a popular soft drink? 50-50? I don't know what's 50% what, grapefruit and 50% starfruit?
Yeah, it's good. Take it from me.
Now, here's your first formula. The sum of the first terms of a finite arithmetic sequence, n times t sub 1 plus t sub n over 2. And it's based on the idea that Gauss did. But a lot of kids get confused on this because in the Gauss problem, the sum of the first 100 is 100 divided by 2 times 1 plus 100. They start associating these two as being the same, and they're not. N is not equal to t sub n generally. Unless
I don't remember what it's called, but unless
it's called the identity sequence.
yeah, it's 1.
T sub n equals n as in the identity sequence.
It's only if d equals 1, right?
Well, it's if d equals 1 and if t sub 1 equals 1. So basically, if your sequence is the natural numbers themselves, then t sub n and n are the same thing. And that's called the identity sequence. So be careful of that. Every other sequence we look at, though, t sub n and n are very different things. It's like x and f of x. They're not always the same, right? When would f of x equal x? When y equals f of x, or when y equals x, which is?
No, it's a one slope line.
It's the slope of one line, and we have a special purpose for this.
Goes to the origin.
Goes to the origin.
Oh, it's symmetry at
For
origin. Odd function.
For inverse function. Inverse function. Odd functions have odd symmetry. Inverse functions are flips over the identity function. Right? We're going to find that there's many tricks you can do with the identity sequence, especially on your calculator. But for right now, find this series. So we're going to prove this. And the proof is pretty straightforward because what you can do is rewrite the formula for this series twice. An arithmetic series starts out with t1 and then you keep on adding d onto it, right? Until you get to t sub 1, t sub n minus d plus t sub n. Now I'm going to do the same thing and write it backwards. So I'm going to put the last term first, and this is what you did with your trick, right? You paired up the 1 with 100 and the 2 with 99. And then count backwards then with the sequence and end up with the first term. The idea then is now we can add these up, add these up, add these up. So we get 2s sub n's equals t sub 1 plus t sub n plus, what about these two? What do they add up to? T sub 1 plus t sub n because the d and negative d cancel out. And then we get another t sub 1 plus t sub n because now the 2d and negative 2d cancel out. Plus dot dot dot. T sub 1 plus T sub n plus T sub 1 plus T sub n. It just remains to see, though, how many of these do we have? 2 times S sub n equals T sub 1 plus T sub n times n, because we actually included every term in the sequence here. We just listed them all backwards. And then you divide by 2. That's the cleanest proof. So it's basically the numbers of pairs times the sum of the first and last term. Okay? That's your formula for the sum of the first n terms. So find the sum of the first 25 terms of this sequence. Step 1, we're going to need the 25th term, because that is in there, right? Right? Find the 25th term, so we have to go back to our T sub n formula, not the S sub n formula, the formula for the nth term of an arithmetic sequence. Remember, that's T sub 1 plus n minus 1 times D. So T sub 25 equals the first term 11 plus 25 minus 1 times the common difference 3. So we get 11 plus 24 times 3, 11 and 72, 83. So T sub 25 equals 83. That just tells us what the 25th term is. We want the sum. Now use the sum formula to find S sub 25. S sub n is n times T sub 1 plus T sub n all over 2. So S sub 25 is 25 times T sub 1 plus T sub 25 all over 2. I'm just taking my time on this so you understand this concept of n and T sub n are very different. We have 25 terms. The first term is 11. The 25th term is 83 all over 2. So we get 25 times 94 over 2. 1175? Okay. Now, what's your TI-89 check on this? Oh, well, let's do this first. We just use this formula, but there's an alternate formula for the sum you can make by replacing T sub n with T sub 1 plus n minus 1 times D. And you know, this happened to you in QCP a lot. When you did all that kinematics, sometimes they combine two of the kinematics formulas to come up with another one. So what was your strategy? To memorize all the basic formulas, or did you memorize more formulas that would save you some time?
Basically substitution.
Okay, fine. And that's your strategy here. So I don't require this formula, but sometimes, for some problems where you have to work backwards, like you're given a sum, this comes in very handy. Because it limits the number of unknowns. Or it might give you an unknown you have already. So if you replace this and put it in here for T sub n, you're going to get n times 2 T sub 1 plus n minus 1 times D all over 2. Now, what are the advantages of this formula? What is it missing? T sub n. So you don't have to in the last term. Kind of like what happened here. So we could have gone S sub 25 equals 25 times twice T sub 1, which was 11, plus 25 minus 1 times the common difference, which we'd see was 3, right? All over 2. And you should get 1175 on that as well. Okay? Now, just because you're in a special class, let me show you another trick. Okay? The TI-89 trick. What was our original question? It said, sum the first 25, right? Of, what was it?
11, 14, 17, 20.
Plus. And that's it. That's all you have, right? Here's how you can trick the calculator into doing all this hard work for you. Are you ready? I don't know if this is going to work. Well, you can use the sum notation. But you need a formula for the nth term first. And we know that, right? 11 plus x minus 1 times 3, right? And then have x go from, careful, x is the index. And that's what you know. 1 to 25. Okay. Okay. If you want to use 0, then you go 0 to 24 and change this to 11 plus 3.
So x is like n then, basically?
Right. And I'm just saying you can use any variable you want as long as you're consistent here. That's why I insist on you giving the second argument there is the variable. In summation notation we call that the index. The thing that points to where you are in the sequence. It's like the input. And all this is the output. It's like f of x and x. Does that check out?
Yeah.
To 1175? Okay. Now, on the next test, I expect you to do everything on the test without a calculator. I'll let you have your calculators to check. And it's good to have a check like this. So if you made one little mistake on how you subbed into a formula, you can detect that. Or at least you're out of time, at least you know you got it wrong. Okay. But I also give some partial credit to the calculator answer, right? Maybe a point. Maybe two. Sum of a finite geometric series. Okay? Sum of a finite geometric series. I have some more complicated formula. I'm not going to prove it now. You can look in the book and use a different trick where you multiply, you take the sequence, multiply the whole thing by r, and then do subtraction. Things cancel out. What I want to talk about is some of the applications of this. T sub 1 times 1 minus r to the n over 1 minus r. I give this alternate form here too. What's the advantage of this alternate form? There's a trade-off. You don't need the number of terms, but you need to know what the last term is. And sometimes that's given, sometimes it isn't. Okay? So keep that in mind. This is handy if you know the first term, you can figure out the common ratio, and you know the number of terms. This one's handy if you know the first and last term, but they haven't told you the number of terms. Okay? Where r equals the common ratio, that should be ratio. Let's just put a little happy face there. And r is not equal to 1.
It can't equal 1 because it'd be infinite then, right? No,
right. If y can r equals 1, if r equals 1, then 1 minus r equals 0, and we're dividing by 0. Undefined, right? Also, what happens if r equals 1? If r equals 1, what formula would you use? It's geometric. R equals 1, so you got t sub 1. What's the next term? T sub 1, T sub 1, T sub 1, and so forth. So, it never changes. So actually, you could think of this as geometric. You could also think of it as the arithmetic with the common difference of 0, right? Well, we don't call that the identity sequence. What did this correspond to in the all functional talk? Horizontal line, right? A constant function. So you could call this a constant sequence, a sequence that never changes. So we don't need this complicated formula for something like that. Give me a formula. No. Times n. Not raised to the n, because actually it's going to be t sub 1 plus t sub 1 over. So it'll just be n times t sub 1, okay? Now, I wouldn't bother memorizing n as a special thing. You can just think that through. Now, let's find the sum of the first 10 terms of this geometric series. So, which one? Choose wisely here. Why? Because we don't know t sub 1. We do know it. Good choice. Good choice. So S sub n, S sub 10 in this case, is the first term, 2, 1 minus the common ratio, careful, negative 3. Get that in parentheses. Raised to the 10th, all over 1 minus negative 3. Now, this you can sub into your calculator. If you show me the substitutions into the formula, I don't want to spend you a lot of time, have you spend a lot of time on arithmetic then. It's beneath you, right? You've got your little helper here, right? So what's your Chinese say? I mean, it's a whole, yeah, it's a whole other. Where's my little check answer thing? Was that the last example? let's do the check with the T89. Check with the T89. How would you do it? A little sum thing. You need a formula for the nth term first. 2 times, careful, what's your common ratio? Negative 3, so get that in parentheses. Raised to, you can use x or n, whatever you want, but make sure you get that in parentheses so it's all in the powers. N, or whatever you use there, right? Going from 1 to 10. What does it say? Check, please. There you go.
Wait, why is negative 3 and minus 1 go to the power?
That's the general formula I'm using here for geometric. T sub n equals T sub 1 times r to the n minus 1. Yeah, and the other one we had in arithmetic. Okay. Okay. There we go. Shut this down, and I'll call up the chart again because they had their dibs, so now you can pick up another one today.
You.